Well, good evening, and my name is Curtis Brown. I am joined once again by Steve Kokoska and Tom Dick. This is AP Calculus Live. We are Monday night calculus session. Yes, this is Monday night. It's our first one in 2024. Really excited to have these guys on here talking about implicit differentiation tonight. Steve has got some great problems for us, so I'm really excited to do that. Drop your name in the chat. Well, not your name, I guess, your location, where you're watching these sessions from in the chat. And again, always invite your students to these sessions. We love to have a lot of students. We had a pre-calculus live session on Thursday where we had about 140 students, and it was a whole lot of fun. We got a bunch of questions asked and answered, and the students seemed to find it pretty beneficial. So just a reminder, always invite your students to these sessions. We love to have them on and answer questions and help them out. As always, stick around to the end. I'll have a professional development certificate link for you if you email me for that. And then finally, go ahead and look down in the description. The link for tonight's problem should have been in there. And then tomorrow morning sometime, I'll call it sometime before lunch, I'll try to make sure that we have the teacher documents up there. So go ahead and watch for that. Anyway, Steve, Tom, I'm going to turn it over to you guys.
Thank you, Curtis. Great to be back with you and Tom again in 2024. Curtis, would you give me the ability to share my
Oh,
screen?
you're right. I forgot to do that. You should have it now.
All righty, there we go. Fantastic. Thank you. I hope that you did your homework tonight, Curtis, because we do have some good
Ah,
questions tonight. A lot of good questions on implicit differentiation, some kind of cool technology too. Some technology that you might think, gee, I didn't know that the calculator could really do that. So Tom has got some cool stuff. Also along the way here, Curtis, I think we've got some good AP Calculus exam tips, some typical sort of problems that have occurred on the exam routinely within the past couple of years. So here we go. Let's consider this curve C, which is defined by this expression. X times y times the cosine of y is equal to x minus y. Well, the very first thing I want to do here with this problem is to see if I can find an equation of the tangent line to the curve C at the point where x is equal to 0. Well, in order for me to do that, I need both a point and a slope. And I'm going to start by trying to find the point. So I've got x equals 0. So to find the y value, I've got to take that x equals 0 and plug it into this expression and see if I can solve that for y. Well, this one isn't too bad. If I let x equal 0, I have 0 times y times cosine of 0. Well, that's just 0. And I think this should be 0 minus y. There we go. And that tells me that y is equal to 0. So right away, I've got a pretty easy point here. There's the point on the curve. So now what I need to do is to find the slope of the tangent line to the curve at that point. Well, I've got to find an expression for y prime or dy dx. Now, I don't think, Curtis, that I could take this expression right here. I don't think I could solve that for y in terms of x explicitly. I don't think I could isolate y, get it all alone on one side of the equation. So this is a typical sort of a problem where we have to recognize that we need to use implicit differentiation. So we take the derivative of both sides of this expression with respect to x, thinking of y as a function of x. Now, perhaps I should have put this problem a little bit later on, but if you look at the left-hand side, this is a little different than some of the problems that we've looked at before. This is actually a product of three terms or three functions. There's an x, there's a y, and there's a cosine of y. And so in general, how do you take the derivative of that left-hand side? Well, you have to use the generalized, what I call the generalized product rule. And remember what that says is you take the derivative of each of those functions separately, multiply by the other two, and then connect it all through a sum. So let's see if we can do that. So here are the three functions. There's the x, there's the y, there's the cosine of y. The derivative of the first function x is 1 times the other 2. The derivative of the second function, well, is 1 times y prime. And Curtis, I'm using a y prime here rather than a dy dx just to make the notation, just to make it a little bit easier. I think if I use a dy dx in there, it just makes it a little bit more cumbersome. So I'm going to use y prime in there times the other two functions, plus the derivative of the third. Let's see, this is going to be a chain rule problem. Derivative of the cosine is minus the sine of y times the derivative of the inner function y prime times the other two. So that's the generalized product. On the left-hand side, I've got the derivative of x is 1, derivative of y is y prime, 1 minus y prime. Terrific. So in the interest of saving just a little bit of time, what I did is I brought the y prime to the right-hand side so that I could collect all of my terms with a y prime in. And let's see, I brought this expression over to the other side because that did not have a y prime in it. Factored out a y prime and did a little bit of division. And there's my expression for dy dx. A little complicated, but this will work out nicely, I think. So now what I need to do is to find or evaluate that derivative at the point 0, 0, at the origin. I'm going to arrow down just a little bit here if I can. I just wanted to comment for a second, Curtis, if I can, about this notation. You know, part of the CED, the course and exam description, is notational fluency. And you know, that's an awful lot of notation in it, but it reads really nicely. It says, find the derivative or consider the derivative dy dx and evaluate it where xy is equal to 0, 0. Now, another way that we might write that, but I think we shy away from this a little bit, is something like this. Y prime at 0, 0. When I write it like that, it kind of looks like a function of two variables. And in AP calculus, we really only deal with single variable functions. But that's sort yes, sir.
We did get a question here about the y prime equals dy dx. Is that necessary or
Absolutely.
needed?
Good question. It is not necessary on the exam. Either one of those notations is acceptable and fine.
Okay.
In fact,
Either's
fine. And I think most students, when they do this, especially in a complicated problem, will use y prime because it just makes the notation a little simpler. So that's a good question.
right.
So, all right, I'm going to evaluate this expression where x is equal to 0, and I'm going to write that in here, and where y is equal to 0, and a lot of good things happen here. There's a lot of cancellation, and I find that the slope is equal to 1. And so that means an equation of the tangent line is just y minus 0 is equal to 1 times x minus 0, or just y is equal to x. And boy, that looked awful at the very beginning, but it turns out very nicely. You would not be expected to do this on the exam, Curtis, but I'm going to do it because we have access to some nice technology. What I did is I used Mathematica to create a contour plot of this curve. So the curve in blue, that's the curve associated with that expression in the very beginning. Now, you'll notice down here, there's a portion of this curve because I ended at -5. I think there's a little bit of symmetry in here. I think if I remember correctly, it goes like this. But the point that I'm making here is I do not believe that this curve crosses the y-axis in any other places. And let's see, at the origin, we found that the tangent line, an equation for the tangent line was y equal x. And you know what? The way that I drew that in there, that looks pretty good. There's some sort of visual confirmation for what I did analytically. So the curve is in blue, Curtis, and if you can see it, the tangent line is in green. Now, again, you wouldn't be asked to do this on the exam, but that's visual confirmation for me because we have access to some nice technology. Tom, do you want to try a little with this before I move on?
Sure, could do that.
Okay.
Um, so with implicit differentiation, I think we should be clear that those types of problems are going to most likely appear on the non-calculator part of the exam. And so these are going to be problems where you're expected to show your symbolic work.
Yep.
That said, as you're working on implicit differentiation problems, you might be wondering, well, is there a way I could use technology to check my work as a confirmation? And we just wanted to show folks a way to do that. Now, if you've got a computer algebra system, you could actually do a symbolic derivative. Really, that's the reason why the implicit differentiation is not on the calculator open part of the exam, because that would give an unfair advantage to folks who had a cast against those who don't. Okay. Nevertheless, you can use calculator to check a numerical value for an implicit derivative. And Steve's example was a case in point. He was looking for the slope of the tangent line to that curve at a very specific point. Turned out to be the origin, 0, 0. And we just want to show how you can compute an implicit derivative at a point on a TI-84. So what I'm going to do is I'll pull up my screen and get my TI-84 shared. And you all can give me some feedback here as to whether that's appearing on your screen.
Sure is, Tom.
Okay.
Looks good.
Great. And so I'm already in my y equals menu. And if you're looking at my y1, it may look really weird. Okay. For one thing, we're used to y1 is usually for a function of x. And so your expression would just have x in it. But notice that my y1 has both x's and y's. Now, what is this thing that I put here? Well, it's actually related to the curve that Steve was working with, except I've rewritten it where I've pulled everything to one side of the equation. Okay, so I've rewritten the equation for the curve, if you want to think about it, as an expression in x and y equals 0. And this is the part that's equal to 0. So it's x times y times cosine of y. That was Steve's left-hand side of his equation. And on his right-hand side, he had x minus y. Well, notice what I've done. I've subtracted x and added y to both sides. So now I have an expression in terms of x and y. And that's an expression that I can actually work with using the numerical derivative to actually evaluate an implicit derivative. And I'll just show you how to do that. So this is our y1. This is actually basically our expression for our curve if we had set it equal to 0. And so I'm going to quit out of that into my calculator. And what I'm going to do is show you an expression that will evaluate to the implicit derivative, provided you have y1 written in the way that I've just said, where you pulled everything over to one side and you're considering that as your expression. So let's take a look at what this will look like. First of all, I need to store the value of both x and y at which I want to evaluate this implicit derivative. Now, I think that was the origin in this case. I'm just going to do 0 store x. And then I'll also do 0 store y. Okay, now that's the point of interest. And now the expression I'm going to show you is it's going to be the negative. And I'm going to pull up a numerical derivative. So I'll go to my math menu and see number 8 down there. There's the numerical derivative. And we're going to take the derivative with respect to x of y1. And that's that expression. It has both x's and y's in it. And so let me pull out y1. And at what x value? Well, we've stored the x value in x. So I'm actually going to put an x here because x is 0. All right. And now I'm going to hit the right arrow key to get out of that. And then we're going to divide by another derivative. This derivative is the derivative with respect to y of y1. And remember that y1, again, is that really an expression of both x and y. And we're evaluating that. Well, we've already stored the value of y in y, so I'll just put y equals y. Now, if all's well and good, when I evaluate this, I should get the same slope value that Steve got. Okay. And Steve, well, we'll do a little drum roll here.
We hope we get one. How about that?
And we got one. Yeah. So
Cool.
that looks good. Now here it's a little bit, I guess, because it turned out to be such a simple value, you may be suspecting this. And I'll be first to admit, because this technique here is kind of a black box, but it is a way, as I'm thinking of it just as a numerical checker. So you're working by hand, paper and pencil, you've gotten a derivative value for an implicit derivative, and you'd like to check it. This is a way to do a check on that. Provided your equation is in the form I mentioned, is where everything's on one side equal to 0. So it's a kind of a handy trick, but it's a way to check implicit derivatives numerically. Okay, so I will stop my share and turn it back over to Steve. Unless there's any questions, Curtis, that you're seeing.
I haven't seen any questions in there, Tom.
Okay.
That's a pretty cool check.
Okay, all right. So back to you, Steve.
All right, thanks, Tom. Very cool. All right, we've got a multi-part problem here. Curtis, I've got some questions in here for you. Let's take a look at this curve C that's defined by this expression, kind of a polynomial in y on the left and a polynomial in x on the right-hand side. And the very first thing I want to do is find dy dx in terms of x and y. Let me just mention that this is a sort of a typical AP calculus curve expression with expression in just x's and y's with no trig, no log, no exponentials. And one of the first things they might do in a free response question is to ask you to find dy dx in terms of x and y. And in fact, what they often do is they say, show that dy dx is equal to, and they will give you the expression. So what we need to do here is to recognize again that we have to use implicit differentiation. So we start off by taking the derivative of the left-hand side with respect to x, thinking of y as a function of x. So on the left-hand side, we've got 2y times y prime minus y prime, derivative of 1 is 0. On the right-hand side, let's see, we've got just a 3x squared, that's the power rule, 6x power rule, and a constant multiple out there. And I'm going to do the same sort of thing here. I'm going to factor out a y prime out of each of those terms, divide, and there's my expression for y prime. Pretty straightforward. A very typical free response question on the AP Calculus exam. Now, there was a question, I believe last year or the year before, where they did this sort of thing. And the next thing they asked for said, well, let's see if we can find the points on the curve C where the tangent line is horizontal. Now, there's some mathematics there, but Curtis, can you tell me what do I need to do in general in order to solve this problem? I mean, what's the general solution technique in order to find the points on this curve where the tangent line is horizontal? What do I need to do? And I'll do it.
I mean, sounds like you might need to separate the variables, but I don't know.
Oh, come on. What's going on with the slope where the tangent line is horizontal?
Oh, sorry. I was monitoring the chat, doing some other things. So thinking about where that tangent line might be equal to 0 then.
Where the slope of the tangent line is 0.
Yeah. Yeah.
So what I need to do is I need to take a look at the numerator in this expression And I need to find those places, those points, x, y, where the numerator is 0. Remember, making sure that the denominator is non-zero. Because if it's an indeterminate form, well, all bets are off. I've got to do something else here. And that's really tricky if I've got both x's and y's in here. So, all right, I'm going to set the numerator equal to 0. And this one isn't so bad. I can actually factor this into the product of two linear terms. And that tells me that x is equal to 0 and x is equal to -2. Is the denominator 0 at any of those places? Well, not quite sure yet because I don't know the value of y at those 2 points. At those two values, excuse me. So I'm going to plug in x equals 0 back into the original expression. I apologize, Curtis. I'm going to arrow up just a little bit. I'm plugging back into this original expression, x is equal to 0. On the right-hand side, I've got 0. On the left-hand side, I've got an expression in y. And son of a gun, that's a quadratic in y. And I tried to factor that and could not do that easily over the rails. And so I went to the quadratic formula and I found two values of y. So that tells me that for x equals 0, just 0, there are 2 points where the tangent line is horizontal. Oh, okay. I'm pretty sure I can see this. I believe that when y is equal to either one of those values, the denominator is non-zero. So I'm good there. So I've got 2 points where the tangent line is horizontal. And what about where x is equal to -2? Well, see, I've got to do the same sort of thing here. I've got to plug x equal 2 back into the original expression. And if I've done everything correctly, once again, I'm left with a quadratic in y, which I cannot factor easily. So I had to go to the quadratic formula again. I've got 2 values of y. So son of a gun, this leads to 4 points on the curve. Gee, I wonder what this curve looks like, where the tangent line is horizontal. Again, I've sort of quickly checked that the denominator is non-zero for those values of y. And it is, it's non-zero. Cool. We're going to put all of this together with a picture here with a graph in a minute, I hope. So let's see if we can find the points on the curve, see where the tangent line is vertical. Okay, Curtis, I'm going to try. What do I need to do there?
Sorry, I had somebody just asked a question in the chat. What was your question?
My question is, what do I need to do now to find the points on the curve C where the tangent line is vertical?
Well, you need to look and see if there's any places where the slope of that tangent line might be undefined.
Beautiful.
Right? You need a division by 0.
Very good. I got to take a look at the denominator, and I need to set that equal to 0. Cool. So that's an easy one here. That leads to y equal to 1/2. And so as before, what I need to do is to take this expression, this value, for y, plug it into the original expression and see if I can solve for x. Now I did that here. And what happens this time is I'm left with an expression in x equal to 0, but it's not a quadratic. This time it's a cubic polynomial. Certainly not easy to factor, if at all. And so what I did, this is kind of a neat problem. It involves some analytics and a technology solution. I actually used my TI-Nspire here to find a value. So I got x is equal to -3.128. And okay, I'm going to add in a little bit more off to the side here in my own notation. I'm going to remind myself that the numerator is not equal to 0 at that value. Okay, I checked it. So there's a vertical tangent line at that point, -3.128, and the y value was 1/2 or 0.5. So using Mathematica, I was able to put all of this together and come up with a curve, sketching this curve in blue. I've got the 5 points that we found here, 4 of them where the tangent line is horizontal, and 1 of them on the left-hand side over there where the tangent line is vertical. Again, sort of visual confirmation that what I found analytically seems to be true. That's pretty cool. Really neat visual confirmation.
What else is
very cool?
What else is kind of cool is that one of those first two solutions where you have 1 plus the square root of 5 over 2. Isn't that a pretty familiar number?
Ooh, very good, Curtis. Wow, what's that called?
Golden ratio,
Golden mean? Very good.
0.618, whatever.
Very good. I'm
Uh,
impressed. Very good.
the
Very
ratio of successive factors in the Fibonacci sequence, if I'm not mistaken.
And in construction, Tom and I know about this. In construction, that is supposed to be the ratio, I believe, of stairs. That is the most pleasing way to walk upstairs. It's sort of the
It's
ratio of the height.
also been put forward as the most irrational number.
Is that right?
The number that is if there was a measurement of irrational, that one has the
That's
greatest.
it.
Yeah.
Okay.
I would suspect pi transcends it. That's an insight.
No, actually, I'll put a link to something out there that I'll send you a link, Tom.
All right, let's try part D. At this point, 0, 1 plus the square root of 5 over 2, which is now Curtis's favorite irrational number, is the curve concave up or concave down? And let's see if we can justify your answer. Now, this is sort of a typical AP calculus question. Also, they might give you a point and ask something just like this, justify whether the curve is concave up or concave down at that point. Now, we've already dealt with this point, but I put in an extra step in here. I just wanted to double check here for something. I know I happen to know that the derivative evaluated at that point is 0. Okay, I was thinking about asking a question about local maximum and local minimum, but I decided not to do that because I wasn't quite sure about how to define local maximum for a curve that's not quite a function. So anyway, we know that the first derivative is 0 there. So what we need to do is to continue with implicit differentiation here, and we need to find y double prime. And we need to evaluate y double prime at this point, at this crazy point, and look at the sign, the SIGN of y double prime. Now I'm going to scribble a little bit off to the side if I can here. Remember, we had an expression for y prime, which was equal to 3x squared plus 6x, all of that divided by 2y minus 1. Now, if I wanted to find y double prime, the sort of gut reaction here, the sort of intuitive thing to do is to just take the derivative of both sides of that, which is fine. Because on the left-hand side, we'll be left with simply y double prime. And on the right-hand side, we have to take the derivative of that expression, but son of a gun, it's a quotient. And so it gets kind of messy. Can you do it that way? Absolutely. But what I decided to do was to multiply both sides by 2y minus 1 to make the left-hand side a product, which would make it a little bit easier to differentiate. And the right-hand side is just a polynomial on x, which is very straightforward. So I'm going to take the derivative on the left-hand side, which is a product, y double prime times the second function, plus y prime times the derivative of that second function. Derivative on the right-hand side is just 6x plus 6, power rule, a couple of times there. And let's see, I think I solved for y prime. This is really 2y prime squared. That's this expression. So I had to bring that to the right-hand side and divide by 2y minus 1. So there's an expression right here for y double prime. So now what I've got to do is to plug in that value of x equals 0, that value of y, 1 plus square root of 5 over 2. And it's actually not that bad. Oh, and by the way, I need to use the value for y prime, and that's where this comes in. I know that y prime at this point is 0. So let's see, that's gone. There's the 6. X is 0. 2 times y, well, the 2's will cancel. There's the 1 plus the square root of 5 minus 1. hey, some really good things happen here. I'm left with 6 divided by the square root of 5. And all I really need to note here to myself is that that expression, pardon me, that value is greater than 0. So that means that the graph is concave up at this point. Remember that concavity, as we've talked about before, concavity is defined in terms of a point, or a curve is concave up or down at a specific point, not an interval. So the graph is concave up at that point. I'm going to go back to my picture if I can here, if I can arrow up just a little bit. There's the point that we had found before. And yep, it sure looks like the graph is concave up at that point. What's the definition of concavity? Well, when you draw that tangent line, there's a neighborhood so that the graph is above the tangent line. And I think that's true. I think you can see that in this picture. Well, that's kind of cool. Tom, I'm going to turn it over to you for just a little bit more technology, and then I'll come back and look at the rest. How about that?
Sounds good, Steve.
Okay.
All right.
Beautiful.
All right. So back on the 84.
Yep, got it.
And just kind of a reminder of what we were doing before. If I go to my y equals menu, I'm not going to actually calculate that numerical implicit derivative again with this, but this is what y2 that you see here is the expression that I would want to use. Notice that Steve's equation was y squared minus y minus 1 equals x cubed plus 3x squared. And so if I subtracted x cubed and 3x squared from both sides, this would be the expression that would be equal to 0, would give me an equivalent equation. But I also wanted to point out something else here. So as we could see by Steve's graph, this was not a function. In fact, that's why implicit differentiation is so powerful, is you can use it on curves that are not graphs of function. What's key is the curve that at the point of interest, there is a function that matches the curve locally around that point. And I just wanted to point out that this is a case where we can actually put together a curve and graph it on the 84 that matches what Steve had. Because notice my y2, the way I have it written, for any value of x, this would just be a quadratic polynomial in y. It's y squared minus y, and then this whole thing with the x in it, minus 1 minus x cubed minus 3x squared, I'm thinking of that as my plus c, okay, on my quadratic. And so if I used quadratic formula, I'm going to go down to y3. Let's see, b is negative 1, so minus b would just be 1. Let me get a parenthesis here. And then it's going to be plus or minus, so I'll put in a plus, square root of b squared, which is minus 1 squared, 1, minus 4ac. So that'll be minus 4 times a is 1, and c is all of this stuff here, the negative 1 minus x cubed minus 3x squared. So let me put all that in there.
Oh. What is going on?
And correct me if I see me making any mistakes
Looks
here.
good, Tom. Looks good.
All right. Let's see, I need one more. And I'll get out from under the square root sign.
Mm-hmm.
And I'll close off that parenthesis and divide by 2, which is 2a.
Gotcha.
All right. So hopefully this looks good. And if I graph this, we should get a function graph, but it should look like some piece of Steve's curve. So let's try a graph. Actually, let me go ahead and turn off these other two functions because I'm not even sure what they would show up as. Okay, so we'll just graph y3. Let's take a look at the graph. Oh, I've got some funky window here. So let me do a zoom, decimal, get back to a reasonable window. And I think that looks kind of like you might think of it as a top half of Steve's curve. Yeah. So how would we get the other half? Well, we go back to y equals. If I had put a minus where I'm waving that 1 plus, remember it was 1 plus or minus the square root. The minus in there, if I made that my y4, that would give me the bottom half of the curve. So kind of neat. All right, so that's one that we're actually able to graph in that way. Now I'm going to show you another way you can check an implicit derivative. That's kind of cool. For this one, I am going to pull out the Nspire.
Okay.
Let me do a stop share, and then I will do a new share with Nspire. Okay. All right. So
got it.
Okay, great. Now I do have an Nspire cast, so it does have an implicit derivative functionality on it. But what I'm going to show you is something you can do with any TI-Nspire. It doesn't have to be a cast Nspire at all. Okay. And so what I'm going to do is take a look at a graph. So let me go back one page here. All right, so I have a graphic screen here, and I'm going to pull up the menu, and rather than do a function graph, I'm going to do graph entry edit. Oops, got off on the wrong one there. Let's see. There we go. Oh, I'm sorry. It's skipping. There we go. Wow. Okay, I'm just going to hit the number 3. There we go. All right. And here are all our different plotters we have. So we have function, we can do polar, scatter plots, parametric. But down here at the bottom is differential equations. And you might be saying, wow, you're really getting far afield here. This is implicit differentiation. But let me pull up the differential equation plotter. And I'm going to show you what I've put in for y1 prime. This is the implicit derivative that Steve calculated. It's 3x squared plus 6x, that quantity over 2. Now you'll see that in place of y, I have y1 because it's for this specific equation. So 2y1 minus 1. So this is a formula for the derivative that Steve found implicitly, and it's in terms of x and y1. And what I want to do is look at a slope field for this differential equation. Okay. So let me go ahead and check that off. And let's hit enter. Not sure what I did there, but we'll try it again. I think somehow it didn't check. Oh, there it is. Okay. Oh, there's the slope field. Great. All right. Not sure why. So this is a slope field. And you say, well, why am I doing this? Well, my original curve should fit this slope field because this is showing me curves that satisfy that differential equation. And that derivative equation that we got from that curve. So kind of working backwards, our curve should fit this slope field. How could we check that? Well, if I go back to my menu to graph entry edit, I'm going to put in a function which was at least the top half of the curve. We just showed it on the TI-84. And let's go up and take a look at it. Okay, this is exactly that thing we plotted on the TI-84, if you remember. It's that 1 plus the square root of 1 minus 4 times all that stuff over 2. If I plot this, it should fit the slope field.
Yep.
And we can take a look, and sure enough, it's really following the slope segments really nicely. And so that's another kind of check. Now, I'm not proposing this, that teachers pull this out as a technique when they're first doing implicit differentiation, but this might be a cool thing to circle back to once you've introduced slope fields and say, hey, by the way, in fact, this is something I often do when I'm teaching, is when I get to differential equations, we have these expressions in terms of x and y for derivatives. I remind my students, as we've seen these before, because when we did implicit differentiation, we often got derivatives that were in terms of x and y. So it's kind of another cool way
Tom,
to check. Yes, Curtis.
before you hop away from this, can't you also go into that slope field, that differential equation, and give it an initial, can't you give it a point and give it a solution curve that goes through?
Yeah, okay.
Get it to calculate one.
Now, that's a technique that basically is going to piece together a curve, but I want you to, before I show that, I want folks to realize that whatever point we get, if we march over here to the left, we're hitting a place where the derivative's undefined. And that technique will just keep stepping over, and we'll get onto different solution curves, ones that don't actually satisfy. But if you want to see what that looks like, let me go to graph entry edit, go back to the differential equation plotter. And what Curtis was referring to is, notice there's a spot down here where I could put 1 point on the curve. I think one of the points Steve had was like a 0,
right,
and the golden ratio, which was
1 plus root 5 over 2.
Yeah, and the 1 plus root 5 is all in the numerator. So sure, I use some parentheses here. So 1 plus the root of 5. Get out from under the square root, and then divide that whole thing by 2. And now when I enter this, it should try to sketch a curve that fits the slope field. But I want you to look what happens kind of to the left of where that vertical tangent was. So you see these brown dots. Oh, they're really hugging the curve very, very nicely. The one that we got in the function plotter, until we get close to that vertical tangent, and then we're seeing some weird stuff. What's happened is it stepped off of this curve and is now hitting other curves that have the same implicit derivative. That's another way to think about it. And
you can add multiple ones of those. So you could go back in and give another one that was like 1 minus the square root of 5 over 2, you know, all of that.
Yeah, and then that would sketch maybe the bottom half, but it would also then
sketch the bottom half, and you'd still end up with a mess on the left over there, because those it's going to try to do stuff for those ones on the left.
Right, because what it's doing is it's continuing the step even though it's gone past. Our curve just simply does not extend any further left than that negative 3.128 or whatever Steve had calculated. But this one, it's kind of saying, well, I'm going to find some point that works, and it may be on a different solution curve. So that's what's happened here. Kind of neat. Okay, I'll turn it back over to Steve then.
Oh, I think what was really cool about this problem was that you could draw that curve by getting this kind of complicated quadratic in y. And that's very unusual. I would like to think that we planned it that way, but that's very unusual. I mean, in general, you can't do anything like that, and your best bet would be some sort of differential equation, slope field, and follow the curve. Which is, yeah.
So another suggestion is that you can actually take that point and drag it around. That was made in the chat. That was suggested in the chat.
So Curtis,
I suggest.
you guys who are much better at this than I am, is there a way to do any sort of thing with level curves and the 3D plotter on the Nspire? Is there any way to drag?
Not that I'm aware of. Tom may have an idea there, but not that I'm aware of.
You mean like an actual contour plot? Or...
Yeah. Yeah. I mean, if you dragged everything to the left-hand side as you have been doing, you really want to try to find all those points X and Y so that expression is equal to 0. So I wonder if you can draw a level curve. Do you know what I mean?
Or alternatively, you could just plot that as a function of X and Y, and then look at where the plane Z equals 0 cuts through your surface, and that would be the same curve. Yeah.
The same curve, yeah.
But you'd be kind of looking at it in 3D, so there'd be...
Yes, a little trickier.
Yeah.
A little trickier.
Okay.
All right, well, cool. Curtis, we've got a couple more here, a little bit of time left. Let's start. This is one of my favorite problems here for implicit differentiation. Let's take a look at this expression. The square root of x plus the square root of y is equal to 4. And one of the very first things you might think about is what values of x and y would be sort of valid here. You know, often I can't do this. I'm not good enough at this to be able to look at an expression and one of these expressions and say, oh, I know that x must be between 5 and 82 and y must be between these two values. Can't do it, but here I think I can. I mean, a couple of the things I noticed right off the bat, I believe, is that certainly x has to be greater than or equal to 0 and y has to be greater than or equal to 0. And I think I can even go farther than that. Because let's see, let's just take a look at x for a second. X can't be bigger than 16. Because if I had the square root of 17, I would have to subtract something off to get to 4. And the square root of y is always a positive number, so that can't happen. So in fact, both x and y must be between 0 and 16. So right away here, I know a little bit about this curve. It's only in the first quadrant, that's for sure. And both x and y have to be between 0 and 16. So I'm sort of in this square in the first quadrant. Well, let's see if we can find an equation for the tangent line to this curve with a point at the point where x is equal to 1. Well, as we did in number 1 this evening, first thing I'm going to do is try to find the point. So I'm going to let x be equal to 1. When I plug it into this expression, I think I get that. I've got to solve it for y. And if I've done everything correctly, I've got y is equal to 9. So my point on the curve is 1, 9. All right, now I've got to find an expression for y prime. And, you know, there is an argument that says, you know, it might be easier to solve this explicitly for y and then take the derivative explicitly. But while we're on implicit differentiation, we may as well do it this way. So I take the derivative of both sides. The right-hand side is easy. On the left-hand side, a 1/2 x to the minus 1. Chain rule here, 1/2 y to the minus 1/2 times the derivative of the inner function y prime. I can get rid of the 1/2. I can multiply everything by 2. Solve for y prime, and I think there's my expression for dy dx or y prime. So I need to find the slope at the point 1, 9 on the curve. So I evaluate this derivative, and there's sort of this expression where I'm evaluating a function at x, y. That's kind of a function of two variables. And again, I think we would understand that notation on the AP calculus exam, but I'm very happy to see something like that. If I plug in a y equals 9 and x equal to 1, I think I get a minus 3. And so an equation of the tangent line to the curve at 1, 9 is this y minus y1, or y minus 9 is equal to minus 3 times x minus x1, x minus 1. And I did a little bit of simplification here to get y is equal to minus 3x plus 12. So if I can arrow down a little bit here, here's what the curve looks like. If you've got color there and the curve is in blue, the tangent line to that curve at the point 1, 9 is in green, and I think you can see it there. Cool, good visual confirmation of what I just did analytically. Let's do a little bit more with this curve. All right, well, I'm going to do a little bit more in general with this curve. I'm going to take a look at the point on the curve where x is equal to a. I think I've noticed, and I don't know whether Tom would back me up on this, but I think that I have noticed on the AP Calc exam recently, over the last couple of years, there have been more problems on the free response portion involving more variables. So solving problems more in general rather than with specific values. So let's take a look at this one. Now, as Curtis said, we're going to be posting the solutions tomorrow morning. So I won't go through all of the details here, but let's make sure we understand what's going on. First thing I need to do is to find the y value that corresponds to that value of x. So I let x be equal to a and solve for y. I get y is equal to that expression 4 minus the square root of a squared. I'm not going to expand that out. I'm going to leave it that way for now. I've got to find the slope of the tangent line at that point. So I evaluate y prime at this point, a, 4 minus square root of a squared. Remember, the slope was minus the square root of y over x. So there's the y value. There's the x value. And some kind of good things happen here because I take the square root of something squared. There it is, 4 minus the square root of a. Should really be the absolute value of that. Okay. 4 minus the square root of a over the square root of a, and a little bit of simplification here. And I think I got that expression for the slope. How about that? So now I'm going to put it all together. And here's an expression for the tangent line to the curve at that point. I'm not going to simplify that in any way. I'm going to leave it like that because I think it's going to be easier to use in this form for my next question. Let's look at C. This sounds like kind of an odd question, but I'm going to try to bring it all together here in a minute. Let's see if we can find the sum of the x and y intercepts of the tangent line found in part C. So, okay, just think about part A for a minute, where I had x equal to 1. Think of that tangent line. It intersects the x and the y axis, so there's an x and a y intercept. And I want to add those two intercepts for any value where x is equal to a. Okay, where x is equal to a, here's the expression for the tangent line. I want to find the y-intercept. So that means I let x equal 0 in this expression. That's what I did right here. That's 0 minus a. And now I'm going to solve this for y. So, all right, I expanded things out, brought everything to the right-hand side. There's my expression for y. There's the y-intercept. Doesn't look too bad. I thought it was going to be a lot worse than that. Now I've got to find the x-intercept, so I have to let x equal 0 in this expression. Pardon me, let y equal 0 in that expression. So let's see. On the left-hand side, that's 0 minus the y value. Yikes, I've got to solve that for x. So let's see, I went through all of that, and you know what? It's not bad at all. It's 4 minus the square root of a. So let's see, the sum of the x and y intercepts would be this value plus this value, which turns out to be 16, which, son of a gun, is 4 squared. Oh, I got to go back a minute here. That's this value right here. So here's a problem for 8 o'clock tomorrow morning with your AP Calculus class. If we did that exact same problem, but we add even one more variable into this, let's call this over here a constant C. We found the tangent line to that curve where x is equal to a. Find the sum of the x and y intercepts. I wonder if that works out to be c squared, or was this just kind of fluky? Cool problem for 8 o'clock tomorrow morning. All right, Curtis,
It's a good one for 8 o'clock tomorrow morning.
We've only got 5 minutes left here. I do have an overtime problem also. I'll kind of rush through this for a little bit, kind of quickly, leave a little bit for you guys to figure out, to think about. And then I'd like to look at the overtime problem because we don't have the opportunity very often to look at BC problems, and I wanted to get the chance to do so. So this one in number 4, we're going to consider the curve defined by this expression in x and y. Find the points in this curve where it crosses the x-axis. So no derivatives involved here. We just have to think a little bit about this. Where the curve crosses the x-axis, y would be equal to 0. So I have to come up here to this expression and let y be equal to 0. And son of a gun, that's not so bad. I can solve that and get 2 values of x. There are actually 2 points on this curve where it crosses the x-axis, plus and minus the square root of 3 and 0. Okay, so part B, I asked to find the equation of the tangent line to this curve C at each of the, points found in part A. And I'll just do a little bit with this since we're talking about implicit differentiation. I want to take the derivative of both sides of that equation and find it and solve for y prime. So pretty straightforward, 2x, I've got to use the product rule there, chain rule here, solving for y prime, y minus 2x over 2y minus x. Okay, we've gone through and done a couple of these problems today. So I'm going to find the derivative at each of those points, find the equation of the tangent line. I'm going to put it all together down at the bottom here, and something kind of cool happens here. It turns out that this curve is actually kind of a tilted ellipse. And it turns out that the tangent lines to these 2 points are actually parallel, which is kind of a neat property. Very cool. So there are some other questions here about find the points where the tangent line is horizontal, find the points where the tangent line is vertical. We'll leave that one. That'll be in the solutions tomorrow morning, but I wanted to take a quick look at this overtime problem and we'll call it a night. This is kind of a neat problem that somebody posted. It was find the integral from minus infinity to minus 5 of 2 divided by that quadratic expression. Well, the very first thing you have to think about when you see this is, well, this is certainly an improper integral because that's an infinite interval. But the other thing I thought about is this x squared minus 2x minus 15. I want to check where that, or if that expression is ever equal to 0. And in fact, it factors as x minus 5 times x plus 3. And that tells me that the zeros there are x equal to 5 and x equal to minus 3. Neither one of those values are in this interval. So I don't have to split this up into 2 separate sort of improper intervals. Now, I want you to be careful when you solve one of these problems on the exam in May, you BC students, make sure that you use the correct notation here. So I'm going to call my original integral I, and it is a limit as a goes to minus infinity from a to minus 5 of this expression. Now, there are loads of different ways to approach this, to attack this solution. Here's what I'm going to do. I'm going to just take a look at the indefinite integral first. So I don't have to worry about that limit yet. I'm just going to take a look at that indefinite integral. And how do you do this one? What's the technique, Curtis, in order to get that indefinite integral? Say the indefinite integral of 2 divided by x minus 5 times x plus 3 dx. How do I do that one? What's the technique called? You remember that one? for 25 bonus points? Partial fractions.
Not even for 100 bonus points on that one.
All right, well, let's use partial fractions, and this is a
partial fractions. Okay.
Very good. And this is a technique that students in BC do need to know about, where the expression in the denominator factors into unique.
I should have guessed that. There's a teacher on Lana, and I'm not going to try to Golemsky, who's been a reader for a long time. Anyway, she was helping another student who had a question in the chat, and I should have just jumped with that, but
okay. Well, in order to do this one, I have two unique linear factors, and in order to separate this, it's pretty standard, pretty straightforward. And in fact, I can write now this indefinite integral like this. How do you integrate both of those terms, or integrating term by term? They're both natural logs. Actually, a very simple change of variables, but we would not expect students wouldn't want them necessarily to write all of that out. So here's the expression, here's the antiderivative for that indefinite integral, and now I'll go back to my original integral I. This is going to be the limit as a goes to minus infinity of this expression evaluated at a and -5. I'm going to plug in the -5. I'm going to plug in the a. This simplifies to the log of 5. And what happens over here? As a goes to minus infinity, I have to think a little bit about what's happening to that rational expression. As a goes to minus infinity, the dominating term in both the numerator and the denominator is a. The -5 to +3 don't mean anything. So those dominating terms here are just a over a. So that expression inside the absolute value goes to 1. So that whole expression goes to the log of 1, which is 0. And so this improper integral converges to that expression 1/4 the log of 5. In this particular case, since that function is above or positive, non-negative, from -5 to infinity, we can envision this improper integral as area under a curve. I've always been fascinated by this expression. It is an area, or it is a region of infinite extent, yet it has finite area, which seems very contradictory to me, but we've just shown that that improper integral converges to 1/4 log of 5. Thanks, Curtis, for those extra couple of minutes. I like that problem, and I'm glad we were able to sneak that in there. Excellent. Thank you.
All right. Well, thanks, Steve. Thanks, Tom, very much. And thanks, Lana. Also, I'm going to give her a shout out in the at the end of the session here, just thanking her for helping that student that was on here logged in. Like I said before, always invite your students. Feel free to bring your students along. Work these problems with your students ahead of time, or give them to them as homework or something of that nature, and even encourage them then to come and hop onto the session, ask questions about the problems themselves or maybe the topic. We will be gathering here again on the TI YouTube channel in about 2 weeks, exactly 2 weeks actually, to tackle our next problem. Off the top of my head, I don't have the...
It is optimization and related
optimization problems next time. So we'll be checking out optimization here in a couple of weeks. We'll get that problem set up and posted here beginning of next week, probably. So looking forward to getting those up there. I will have the teacher documents up here in the morning. And finally, if you watched all the way through, don't forget to email me, curtis@ti.com, and I will send you a professional development certificate, rather a link to generate one. So I'll put that, I'll put my email in the chat one more time, just to be sure. And otherwise,
Curtis, if I may add one thing, I'd like to encourage people to, if they have any specific sort of questions that they'd like us to look at.
Oh, yeah.
Both analytically or with technology, I'd like to encourage people to send those questions to you, and I know you'll forward them along.
Yeah,
we'd really
absolutely.
like it from students, from teachers, we'd appreciate that. I mean, we've been getting some
Absolutely.
from the Facebook group, but we solicit questions too.
Yeah, for sure. We do pay attention to the Facebook group. I know Steve and Tom go out there and look. But anytime you have a question or something that you would like to see us address during these sessions, feel free to email me, Curtis at TI, and be happy to bring that along. All right. Well, thank you very much. We will be seeing you here in exactly 2 weeks.
Very
All
good.
right.
Thank you.
Have a great night.